All right, welcome to the Explainer. Today, we're diving into a super important group of molecules that are, well, hiding in plain sight. They connect things in our world you would never, ever expect. Let's jump right in.
So, I want to kick things off with a question for you. What in the world could a ripening banana and a plastic water bottle possibly have in common? I know it sounds totally random, like a riddle, but the answer is pure chemistry.
You see, the link between them is a very special class of molecules. These guys are the chemical workhorses, doing the job behind the scenes in both nature and in our factories. And the star of this whole show is the alkene. And if there's one thing you need to know about alkenes, it's this. They have at least one carbon-to-carbon double bond. This isn't just some tiny detail. It's the secret sauce. This double bond dictates literally everything about them. That double bond even changes the molecule's basic formula. Okay, look to the left. Saturated hydrocarbons are totally maxed out, holding every single hydrogen atom they possibly can. But alkenes, on the right, while they're unsaturated, because of that double bond, they have two fewer hydrogens. They're not completely full. So let's meet a few members of the family. Here are the simplest alkenes. Ethene, with just two carbons, that's actually the plant hormone that makes our banana ripen. Then you have propene, a key ingredient for making all sorts of plastics. And as we add more carbons, you get butene, pentene. You see the pattern, right? The name always ends in ene. Now, that double bond is so important, it basically runs the show when it comes to naming these molecules. You can't just name the carbon chain. Nope. You have to say exactly where that powerful double bond is located. Naming an alkene is a pretty straightforward three-step process. First up, find the longest carbon chain that actually includes the double bond. That's key. Second, you number that chain. But you have to start from the end that gives the double bond the lowest possible number. Its location is priority number 1. And finally, you just name and number any branches alphabetically, just like you would for any other hydrocarbon. Okay, your turn. Let's put those rules to the test. What do you think is the official IUPAC name for this molecule right here? Go ahead and hit pause if you want a second to figure it out. All right, you ready? The answer is 3-ethyl-4-methyl-3-hexene. So let's break that down real quick. Hex tells us the longest chain has 6 carbons. That ene ending screams that it's an alkene. The 3 right before hexene tells us the double bond kicks off at carbon number 3. And then we just have our branches, a methyl group on carbon 4 and an ethyl group on carbon 3. See? Simple as that. But wait, that double bond does way more than just affect the name. It fundamentally changes the molecule's shape. You see, a single bond can spin freely, kind of like an axle. But a double bond? It's rigid, it's locked in place. And that rigidity leads to some really fascinating consequences. This whole locked-in-place thing gives rise to something called geometrical isomers. These are molecules that have the exact same formula, connected in the exact same order, but they're arranged differently in three-dimensional space. Think of them like twins who are stuck in different poses. Just look at this classic example. Both of these molecules are 2-butene, but in the cis version on the left, see how the two methyl groups are on the same side of that double bond? Then look at the trans version on the right. They're on opposite sides. And because that double bond can't rotate, these are actually two completely different molecules with different properties. So when does this happen? Well, two things have to be true. First, you need that restricted rotation, which our double bond gives us. Check. Second, and this is super important, each of the two carbons in the double bond must be attached to two different groups. If either one of them has two identical groups attached, say 2 hydrogens, then you can't have cis or trans. It's a no-go. And now for the main event. We've seen how the double bond affects the name and the shape, but its most important job by far is in chemical reactions. That unsaturation, that double bond, it makes it a total hotspot for chemical activity. Think of that double bond as being under a little bit of tension. One of those two bonds can break open really easily, which creates 2 new open spots for other atoms to come in and attach. This is the whole idea behind addition reactions, where you literally add things across that double bond. First up is hydrogenation. It's exactly what it sounds like. We're adding 2 hydrogen atoms. The double bond pops open, a hydrogen attaches to each carbon, and boom, our unsaturated alkene becomes a fully saturated alkane. This is literally how liquid vegetable oils are turned into solid margarine. We can do the same exact thing with halogens, like chlorine or bromine.
We call that halogenation. Again, the double bond opens up and a halogen atom grabs onto each of the carbons. It's a really predictable, straightforward addition.
Okay, but what happens when we try to add something that isn't symmetrical, like hydrogen bromide? Now we're adding one hydrogen and one bromine. So we have a choice to make, right? Which carbon gets the H and which one gets the Br? Well, the answer comes from a guide called Markovnikov's rule, and the way to remember it is absolutely brilliant. The rich get richer. All you do is look at the two carbons in the double bond. The hydrogen atom will always go to the carbon that already has more hydrogen atoms attached to it. The rich carbon gets richer in hydrogens. Simple. And this rule is a total workhorse. It doesn't just work for hydrogen halides. It also applies to hydration, which is just the fancy term for adding water. When you make an alcohol from an alkene, you're adding an H and an OH from a water molecule. And you guessed it, the hydrogen atom follows Markovnikov's rule, adding to the carbon that's already richer in hydrogens.
So as we wrap up this explainer, if you remember only one thing, let it be this. Every single thing we've talked about, every property, every rule, it all comes down to one single crucial feature.
That one carbon-carbon double bond. It dictates the molecule's name, it dictates its shape, and whether it can have those cis strands isomers, and it's the key to its incredible reactivity. It truly makes alkenes one of the most versatile and important building blocks in all of chemistry. Which brings us right back to where we started. The next time you pick up a plastic bottle or see a banana ripening on the counter, I hope you'll think about that powerful, shape-defining, reaction-driving double bond that makes it all happen.